So this is the lecture on section 3.1 on position and displacement. I'm actually going to start us off looking at time, which we'll symbolize with t, and duration, which we'll symbolize as a delta t. And if you've not seen this triangle before, that is the capital Greek letter delta, which is what we often use in physics and math to symbolize change. So this is time and this is change in time. So as an example, this would be something like the meeting time 2:30 p.m. And this would be how long it lasts, 2 hours and 30 minutes. So even though these are similar, they don't mean the same thing. This might be when your class time starts, and this might be how long your class is. So for this, maybe the key difference is for this guy, you've got to know when noon is. You've got to know what time zone you're in. In other words, you need to know the origin, which just means you know when 0 is. For this guy, you don't. As long as you get to class at the right time, wherever you start, whatever time zone you're in, it's going to last the same amount of time, no matter what it says on your clock. So here we don't need the origin. We don't need to know when 0 is. Something similar is going on with position, which I'll call x, and displacement, which is your change in position over a certain time. Now, position is what we call a vector. So I'm going to put a little arrow on top of it, as is displacement. So that means vector, that little arrow. And what a vector is it's something you have both a size, maybe 2 meters, and a direction, 2 meters to the north or 2 meters to the south. So if you have a vector, both the direction and the size are important. And for the position, just like for the time, we need to know where the 0 position is. We need to know where the origin is. Whereas displacement, that's just how far we've gone. That it doesn't care where 0 is. It just cares where we started and where we stopped. It is invariant to the origin if you're going to use very fancy words. So let's see how that works. So we've got a displacement line. We'll make this our origin to start, and this will be the positive x direction going this way. So if this is where we happen to be, if this point's our origin, then this guy is our position vector, whatever distance that would be. But on the other hand, if this is our origin, you can see we'd have a different length for our position vector, even though we're standing in exactly the same spot, because the position vector always starts at whatever origin you're using. All right. Then say if we started here, this is our starting position, and we ended here, that would be our ending position, then our displacement would be, we'd start at our starting vector, we'd travel to our ending vector, and this here would be our displacement. And you can see that wouldn't matter whether this or that was our origin. Our starting position is this size if that's our origin. Our starting position is this size if that's our origin. And the ending one is this one or that one, depending on whether you're starting with the black or the red origin. But the displacement is always the same. So that's what I mean when I say position depends on which origin you're using, but displacement doesn't. Now, we talked about these guys being vectors. Let's do a little better definition of vector. That means it has a magnitude, which is the size Here, it's how long those arrows are, and it also has a direction, which way those arrows are pointing. They're all pointing in the positive direction for this example, so these guys are all positive vectors. And here, mathematically, we symbolize that as a plus or minus sign. If you're going in the positive direction, if your arrow points in the positive direction, you are a positive vector. If your arrow points the other way, you are a negative vector. Just to get some practice with that, let's draw out our position line again. If, say, we start here and end there, well, both of our position vectors would be positive. They are both in the positive direction from the origin. But our displacement vector, where we start at our starting position and travel to our ending position, the displacement vector is negative in this case. So positive direction means positive vector, negative direction means negative vector. We can also look at this as a graph. So I am going to draw my graph like this. This is going to be my origin, where position, which I will draw along this axis, and time, they both equal 0 here. So position is 0, time is 0, and then I can draw out my path. Maybe my position goes like this for a while, I stay in one place, and then I travel slowly down towards the origin and I stay in one place, and then I travel quickly in the positive direction away from the origin and I stay in one place. So right here, I'm staying in one place. My position, the value on this axis, doesn't change as time goes forward. So I have 0 displacement here. My ending and starting position are the same. Here, I go from farther away from the origin in a positive direction to closer to the origin. Still in a positive direction, but I've gone from further away to closer. I'm traveling in the negative direction here. So this guy is a negative displacement happening right here. Here I'm starting closer to the origin and then I'm traveling out farther away in the positive direction. So this guy is a positive displacement. And then these guys, well, I'm also staying in one place. My position isn't changing as time travels on, so 0 displacement there. One final thing for this section is how quickly your displacement changes. So looking at your displacement over the duration of that displacement, how long it took you to get wherever you're going. And that guy is equal to what is called the average velocity. And velocity is speed, how quickly you travel some distance. And it's also, as you can see by the little hat here, it's also a vector. So it's also the direction that you travel in. Are you going 90 miles an hour north or south? Those are different because velocity cares both about the size, the magnitude, and the direction. And as you can see here it takes us a relatively long time. Let's mark that out in blue. So there's our duration. Here's our displacement. The slope is pretty shallow. This number is pretty small. This number is relatively big. That's going to give us a small average velocity. So that is slowly we are walking back in the negative direction. Whereas this one, well, that's how long it takes us to do it, and that's how far we go. So we have, that's our displacement, here's the duration, and so delta x is a big number in that case, and delta t is a relatively small number, so we're going to get a big average velocity. So we are traveling quickly in the positive direction here.